Okay, so section 8.2 deals with series. Okay, let me just hold on here, change the font a little bit here. Yeah. Section 8.2 deals with what are called series. Now, let's first of all look at a sequence. So you had some practice in your homework with sequences. So a sequence is an ordered list of terms. So let's say you had a half and a fourth and an eighth and a 16th. What would the next term be, you think, for this sequence here? That's right, Jonathan, 1 over 32. And the next term of the sequence would be that's right, 1 over 64, and it keeps going. Okay, so if we think about the terms of the sequence, this is the first term, second term, third term, fourth term, fifth term, sixth term, and so forth. So indeed, the nth term would be 1 over 2 to the nth power. That's the nth term. And does this sequence converge to a number as n goes to infinity? Does this sequence here? That's right, John. It has to go to 0. So there's multiple ways to show that. You could do it algebraically, but also you could just go and plot the sequence in Desmos and observe that the sequence approaches 0. I mean, the denominator keeps getting larger and larger and larger, right? So the sequence has no choice but to go to 0. How many use Desmos to help them with some of the section 8.1 problems? Okay, good. And that's Avery and Jonathan and a number of you, and that's fine. That's certainly fine on the exam as well for section 8.1 to use Desmos, help you get answers. That's fine for section 8.1, the sequences. Now, so we know what a sequence is. We know what a sequence is. Now, what is a series? What is a series? What does that mean in this context? Well, a series is when you do this. If we were to take the terms of the sequence, a half, a fourth, so this is a series. Okay, if I take a half and a fourth and an eighth and a 16th and a 32nd and so forth, and I added the terms. Okay, if I add the terms of the series up, okay, so the way the book has this actually is if we can write it a little bit differently here. We can have a half plus a fourth plus an eighth plus a 16th plus a 32nd plus dot plus 1 over 2 to the nth power plus dot. That's another way to write the series. And what you're doing is you're adding up from n equals 1 to infinity terms of the sequence. So in other words, if we write the series out, this is the long way to write it. Okay, but we know what we're doing there. We're adding the terms of this sequence here. And that's a series when you add the terms of a sequence. But we can write that series in short notation like this. And this symbol here is the symbol called sigma, the Greek symbol sigma. How many have seen that before? Maybe in pre-calculus, that summation sign.
It
Okay,
means the
Leah
sum.
has. It means sum. Sigma means find the sum. That's right. Very good. Find the sum. So just like we're interested if sequences converge to a number, we're also interested in a series, if a series converges. So we know that that the sequence here converges to 0. We know that. But what about the series? Does the series converge to 0? Well, this problem is a little bit like when you studied improper integrals, when you had an area that kept building up and building up out to infinity. Some of those integrals diverged, some of those improper integrals converged. It's the same with series. We are adding an infinite number of terms. Now, the terms, in order for the series to converge, the terms do have to get smaller and smaller. They have to approach 0, right? But that doesn't mean the series is going to converge. So it's really a fascinating topic. And what I want to do is now go into the book, section 8.2, and carry on this conversation regarding this particular series that I'm focusing on. Are there any questions before I do that? Okay. Okay, well, let's go ahead and do that then. Okay. So this is how you see in the box there, box 1. If you add the terms of a sequence, you're adding the first term, the second term, the third term, the fourth term. I mean, this is what you're just adding the terms of the sequence. And when you do that, you get a series, or what we call an infinite series. And we can denote that with the shorthand notation, the series notation, where you use the Greek symbol sigma. And they ask, does it make sense to talk about the sum of infinitely many terms? Well, you know, if you had, okay, let me just, like here, they say, okay, well, let's say you wanted to add the series 1 plus 2 plus 3 plus 4 plus 5, you know, I mean, in other words, you're adding the terms, you have a series. The sequence is 1, 2, 3, 4, 5, 6, 7, 8, 9, and so forth. If you wanted to add the terms of that series, you're going to see that the series doesn't converge, right? Because you're adding more and more terms. You're adding an infinite number of terms, and the terms keep getting larger and larger. So this highlighted series in yellow, 1 plus 2 plus 3 plus 4 plus 5 plus and so forth, that series would have to diverge, right? That series has no limit. There's no finite sum for that series. However, on the other hand, hold on here, if you have this series here, which is a series that we talked about in the whiteboard, Okay. Well, it turns out that series converges. That series converges. And what does it converge to? Well, the series converges to 1. So we're adding an infinite number of terms, an infinite number of positive terms, and this series, the series where n goes from 1 to infinity of 1 over to the 2nth power, that's going to equal 1. We did not do any integration here. We're just saying when we add the terms up of the series, it equals 1. Now, the question is, how would we intuitively see this? Okay, well, one way to intuitively see that is since you understand about sequences from section 8.1, we could take what are called partial sums of that series, partial sums, and study how the partial sums behave. A partial sum is the sum of the first n terms of the series. So if I go down here a little bit, okay, you have, all right, so you have n equals 1, 2, 3, 4, 5, 6, 7, and so forth. And on the right part of the table, they have the sum of the first n terms. So when n is 1, the sum of the first term, its sum is just the first term, a half. When n is 2, we're getting the sum of the first two terms as 0.75. Now, how are we getting 0.75? When n is 2, the sum of the first two terms is 0.75. How are we getting that?
Is it going to be like 1/2 plus 1/4?
That's exactly right. Good, Clea. Good, Jonathan. 1/2 plus 1/4 is 0.75. 0.5 plus 0.25 is 0.75. When n is 3, the sum of the first three terms would be a half plus a fourth plus an eighth. Okay, that's like 0.5 plus 0.25 plus 0.127. Hold on, an eighth. I should know that. Yeah, that's a half plus a fourth plus an eighth, and a half plus a fourth plus an eighth is the same as 0.5 plus 0.25 plus 0.125. That will equal 0.875. So you see, we can study how these partial sums on the right side of the table, what they do. We can look at what's called the sequence of partial sums, the sequence of partial sums. And this is formally how we establish if a series converges or diverges. We look at its sequence of partial sums. And based on this sequence of partial sums, okay, what do the partial sums on the right appear to be approaching? What number?
1.
1. That's right. And so this means then that the series here equals 1. Okay, that's what that means. Yes, question, Clea.
So for this part that we're talking about, we say that the series is like as when it approaches 1, right?
The series equals 1. The series it actually equals 1 because the series says, okay, take your terms of the sequence, and which are an infinite number of terms, and add them up. Keep adding them, add them all up, and you will actually get 1.
Okay.
Yeah, it's a fascinating idea. Fascinating idea. And you know, we can be more formal here. Are there any other good questions before I move forward here? let's see. Jonathan asks, how would you not get 1 if it goes on to infinity? Well, I mean, it's just you look at the sequence of the partial sums in this case, and since the, I mean, if this is sort of formal, but if you look at the series, you can study the series by taking the sum of the first term, sum of the second term. So I mean, take the partial sums like they do in the table here, and study the partial sums themselves form a sequence. So you know how to handle sequences. The sequence of partial sums appears to approach 1 in the table on the right. I mean, look at the 10th partial sum. That's point. We'll look at the 7th partial sum, which is the first sum of the first 7 terms. That's 0.99218. 75. So that might make you think, okay, maybe 1's the going to be the sum of the series. The 10th partial sum is 0.9990234. So the sequence of partial sums is going to approach 1. Now, the thing is, I understand, like, that's not like, that's just, I'm telling you that, right? But intuitively, you can see that, hey, that seems to be what's happening here. And that's the idea. That's the idea. But of course, and so the series would converge, and this series here, let me bring it up. This series here would converge, and it would equal 1. Now, if the series, and that's the sum of the series. If the series doesn't converge, it diverges. Okay, so they go into, like, here's the definition in section 8.2 of a convergent series and a divergent series. And this is, I mean, take a moment to look at that. Okay. Are there any, again, we're going to be learning, there are a lot of special kinds of series where we can determine, I mean, there are some special series where we can actually get formulas to determine what their sum is and if they converge or diverge. When it converges, Clea, you just write S. S is the sum of the series. Well, you're actually going to find the value of the sum. So I'll tell you what, let's go to an example here. Let's go to an example. Now it's a good time to bring in one of my examples. Let me give you a moment to copy this example down, okay? And then we'll go over it. Okay, take a moment to copy the example. Okay, so let's take a look at what we have here. So, of course, n goes from 1, 2, 3, 4, and so forth. So in part A, we want to determine if the sequence is convergent. In part B, we want to determine if we add the terms of this sequence, will the series then converge? Okay, that's what we're going to do. Yes, question.
Yeah, so Professor, before we start, if you don't mind, can you explain the difference in the questions, like why they're different?
Why they're different? Well, I wanted to have the two different questions. I wanted us to do them together because I think it will. I think it'll help you see what the difference is between a sequence and a series.
Oh, okay.
That's why. And let me ask you this. The sequence, and this is how we denote a sequence with the brackets. So based on this formula here, based on that formula, and I guess I have to sorry about that. Let me just sometimes you have to erase. Okay, one moment. Right, so it's understood n goes 1, 2, 3, and so forth. Okay. And okay, what's the first term of this sequence here? What's the first term? When n is 1? 4/4.
Yep.
Which is 1. That's right, John. That's right, Clea. 4/4 equals 1. What's the second term of the sequence?
Uh, 8, 7.
That's right. What's the third term of the sequence? So, of course, 8/7, by the way, that's just because you go 4 times 2, all divided by 3 times 2 plus 1. That gets you your 8/7. 8/7. The next term, yep, next term will be 12/10. So, naturally, I'm just, writing out terms of the sequence. The fourth term would be what? That's right. Good, Victoria. 16/13. So, this is the sequence. And it might be a little hard to see what the sequence converges to, but let me ask you this. If we look at this sequence, okay, what n, the two n's in the two terms with n in the numerator and denominator, as n gets large, those terms get big, right? So when those terms get big, that's right, John, does the one really matter that much in terms of what the what the term computes as of the sequence?
No.
It doesn't. So that's right. So you could kind of look at this like as the relevant behavior when n is large is 4 over n divided by 3 over n. And that equals what would happen to the n's? I mean, we can't cancel them because we can't simplify them out because we have the +1 there. But 4 times n over 3 times n equals what? That's right, Jonathan, 4/3. So this sequence is going to converge to 4/3. Let me go ahead. So part A is yes. Now let me go to the next page and be a little formal here. Let me give you a moment to copy this down. Yes, question, Clea.
Yeah, so I'm just wondering, like, since this is determine whether the sequence is converging or not, can we do it as we did with the homework? So, like, we can use Desmos?
You may use Desmos. Yes, you could plot the sequence and determine that the sequence converges to 4/3.
Yeah.
And you know, WebAssign though, now Desmos would probably give you something like 1.3333, and it'll count that wrong. It wants the fraction, you know, it wants the simplified radical form of the answer. So you
Okay.
always have to be, you know, careful about that.
Yep.
But yeah, you could use Desmos to help you.
Yeah, but
Yeah,
um,
go ahead. Go ahead.
yeah, I was just gonna say, if we use it on the exam, like when we show work, how can we like write, like just say we use Desmos?
Yeah, that would be fine. That
Okay.
would be fine for the sequence problems, section 8.1. If you use Desmos, um, that would be, I think, I mean, if there probably, I'm sure there's some sequences that you saw in your homework and you probably looked at some of the help videos that, you know, where just, you know, plotting the sequence maybe wasn't quite enough to get the answer, but definitely you can use Desmos to help you. And some of the sequences, certainly just using Desmos would be fine. Um, and for this one here, you know, I prefer to just sort of do it algebraically. I mean, I have 4n divided by 3n plus 1, that's the nth term. And what I can do is, see, to help me feel better, is I can multiply by 1 over n on the top and the bottom. How many maybe did that for some of the sequences in their homework? Okay, Susanna did. Sure. And what's going to happen is then the ends here are going to simplify out, and you're distributing 1 over n to both of these terms here. And so that's going to give you, well, I mean, if I put in an extra step here, this is going to equal the limit as n approaches infinity of 4 over 3 times n over n plus 1 over n. Let me make that a little bit nicer here. And so that's going to get you then here. And clearly, as n gets large, 1 over n, that's going to go to 0. Has no choice, right? And that'll leave you with 4/3. So in the limit of the sequence is 4/3, and we say the sequence converges to 4/3. So the sequence of terms converges. And it converges, the sequence converges to 4/3. So you see, this is how we denote a sequence. We don't use the summation sign for a sequence. A summation sign would mean that we're doing a series. So if I wanted to be very formal about this, and when I take the limit, I'm going to get right 4/3 plus 0. And that gets me then the 4/3 here. So, are there any questions on this one? See, I think that's easier than even going to Desmos. I think it's just easier to sort of to get the answer that way. But that's fine. All right. Well, now let's look at the series. With the series, what we're doing in part B is we're going to add up the terms. Okay, add up the terms of the sequence. Let me just hold on. Yeah, in part B, we're going to add up the terms of the sequence. So let's go to part B. So the series now, okay, this series is just, well, what I did was I wrote down the first 4 terms of the series, and then I'm going to add. But the series cannot converge; it has to diverge, because the limit of the nth term of the series is equal to 4/3, and that's not 0. This is what's called test for divergence. If you have a series, in order for the series to have a chance to converge, I'm not saying it does converge, but in order for a series to have a chance to converge, the terms of the series have to approach 0. They have to approach 0. But the terms of this series approach 4/3, because the series, the terms of the series come from that sequence, and the limit of the sequence of terms is 4/3. So the series is basically, as n gets very large, the series starts looking like I mean, basically, here, I'll write it here. What, to sort of give you an intuitive feel. So, you know, the series is 1 plus 8/7 plus 12/10 plus 16/3, and then we keep going, and we keep going. And when n is large, the terms of the series sort of they behave like this: 4/3 plus 4/3 plus 4/3, and so forth. Okay, so this is approximately how our series is behaving. And you see, when n is large, the terms of the series are all close to 4/3, and if you add an infinite number of 4/3 together, you're going to get infinity. So the series has to diverge. Yes, question, Clea?
Yeah, so like you said for it to converge, it needs to approach 0.
For the series to have a chance to converge, the terms of the series need to approach 0. Yes, that's correct.
Yeah,
And
but
our terms of our series approach 4/3.
yes,
They don't approach 0.
but on the example we saw in the series, like on the book, we said that if the series approached 1, so it converges, right?
Well, in the book, the introductory example in the book, we had a we were looking at this. We were looking at the partial sums of the series and looking
Yeah.
at the sequence of partial sums, and the sequence converged to one. That's another way to show that a series converges, but it's often difficult to employ. So, I mean, we're going to have ways to find out quicker ways to find out if the series converges. Like for instance, I'll give you an example here. Let me go to the ebook here. I'll give you an example.
Yeah, I see. But like, why in the book we said that it converges because it goes to one, but here we said it diverges, even though it goes to 4/3.
Well, the terms of the sequence start acting like about 4/3. They're about all equal to 4/3. As you go further and further into the sequence, as you go out further and further into the series, the terms of the series are going to all be close to 4/3 because the terms of the series are dictated by this formula 4n divided by 3n plus 1. So the terms of the series are going to approach 4/3.
Yes.
And if you add up 4/3 and 4/3 and 4/3 and 4/3 and do that forever, you're going to get infinity. You're not going to get a convergent series. So this approach is a little different. We didn't look at a sequence of partial sums like I showed you in the ebook. That's just sort of an introductory kind of example in the ebook or textbook to give you a feel of the situation. Let me show you something else here. Hold on. I think another example will be illustrative. So, okay, we have in which is a common series, is a series called a geometric series. A geometric series can be written a certain way. Okay, and I don't want to get caught up into the details here, but let me just go to a formula here. Okay, this is a formula that says if you have a geometric series, the terms of the series are a times some common radius to the n minus first power. The series, if the common radius, if the absolute value of the common radius is less than 1, then the series converges and its sum equals a over 1 minus r. So the highlighted gray box there, I think you should go ahead and write that down, in your notes, and then we'll do an example. Okay, we call this a geometric series, and geometric series have what's called a common ratio. All right, let me go to one of my good examples here. Okay, and one moment here. Let me just check one thing here. Yeah, let me give you a moment to copy this example down. Okay, so what you have here, of course, is a series. And why is this a series as opposed to a sequence?
Because we're adding all of the numbers.
That's correct. Very good, Clea. We are adding our terms we are adding the numbers. So a geometric series, any geometric series, has associated with it what's called a common ratio. And let me just change the font here. Hold on. Okay, any geometric series has common ratio. And we call this common ratio R. Now, if we wanted to find the common ratio, well, let me all right, let me show you how we would do this. So one is a sub 1. A third, that's the second term of the series. So 1 is the first term of the series. A third is the second term of the series. A ninth is the third term of the series. 27th is the fourth term of the series. By the way, what would the fifth term of the series be? 1 over what? 1 over 81. That's right, Yonatan. And it keeps going. Now, suppose that we took the second term and divided it by the first term. What would that equal? Second term divided by the first term. Well, that would be a third divided by 1. What is a third divided by 1?
1/3.
1/3, right. That's right, Clea. That's right, Daniel. Okay, now you notice what am I doing here? When I take a half divided by, when I take the second term and divide it by the first term, that's a ratio, right? That's a fraction. I'm taking a ratio of 2 terms. What if I take the third term and divide it by its previous term? So I take, the term on top, I divide by the term that comes before it.
1/3, yeah.
That'll equal 1/3 again. Absolutely. Absolutely. That's right, Daniel. That's right, class. So a third is a ninth. And if I divide a ninth by a third, that'll equal 1/9 times 3 over 1. You multiply by the reciprocal when you divide fractions. That's going to get you 3 over 9, which is a third. Okay, and incidentally, if you were to take the fourth term and divide it by the third term, you would again get a third. So this has what's called a common ratio. Common ratio means you take a term of the series and divide it by the previous term, and that ratio is always the same. It's a common ratio. So in this case, our common ratio is equal to 1/3. Now I have this written on the next page, but I wanted to just, let me go to the next page. It's all here. Okay, and at the top, I think maybe, well, I'll let you copy, but again, our series was 1 plus a third plus the 9th plus the 27th plus an 81st, and so forth. Okay. Common ratio is a third. Now, oftentimes, well, let me give you a moment just to catch up here. Okay, so a lot of times we want to take our series, okay, we want to take our series and we want to express it with, as in brief notation, with a summation formula. Now, in terms of these, geometric series, the first term is always denoted, we call that A. Okay, so A is the first term. R is the common ratio. Common ratio, R. And we can write our series, this geometric series here, with this summation notation. I don't know why it's doing that. Hold on. Something goofy. Don't need goofiness here. Okay. I mean, this is our series, the series from n equals 1 to infinity of 1 times 1/3 to the n minus 1 power. Now you might be wondering, Dr. Diddy, why are we doing that? Why are we doing this? Let me just jump to the book. I'll come back here. I'll come back. When you have a geometric series, oh yeah, well, yeah, we actually mentioned this, right? The sum of a geometric series a geometric series, so long as the absolute value of its common ratio is less than 1. Okay, this is from section 8.2 in the textbook. For a geometric series, so long as its common ratio, the absolute value, is less than 1, the series will converge, and it will converge to the value A divided by 1 minus R. R is the common ratio, and A is the first term. Okay, so if I go back to the file here, hold on. Yeah. Okay. I mean, what I did here was I rewrote the formula. I rewrote the series in terms of this sigma notation. But I could just go really from here to here. because I know the first term A is equal to 1, and the common ratio is equal to 1/3. So what I'm trying to say, let me be even more clear here. What I'm trying to say is this. This series has a finite sum, and the finite sum is 1 over 1 minus 1/3. Because the common ratio is less than 1, this geometric series converges, and it converges to the finite sum of 1, which is the first term of the geometric series, divided by, in the denominator, 1 minus 1/3. 1/3 is the common ratio. And so this series here will equal, well, what will it equal? We can be very clear on this. It's going to equal 1 divided by 2/3, and that's 1 over 1 divided by 2/3. That's 1 over 1 times the reciprocal 3/2, and that just gets you 3/2. So we say the series converges to 3/2. That's the sum of the series. If you were to program this series into a computer using this formula, okay, which is a formula for the series, right? It's a formula, just like people have names, series have formulas, right? If you were to program that into the computer and have the computer run like forever, eventually you'll get a value, a decimal, very close to 3/2. And eventually it'll round it to 3/2, right? Okay, are there any questions on that? I'm going to do another one on the whiteboard here, and then we'll go on our break. But these are geometric series here that we're looking at right now. All right, let me try this one with you. Let's say you had a series like this. Let's say this is your, I don't know, it should, there. Let's say this is your series. Let's say you had 1 minus 3/2 plus 9/4 minus 27/8 plus, you know what the next term would be? So this is an alternating series. Can you think what's the next term going to be?
(81/16).
Good. 81/16. That's right, Clea. And actually, OPM, you're right, except it's going to be positive. Okay, is this a geometric series? Is this series geometric? Yonatan says yes. How do you know, Yonatan? All right, common ratio? What's the common ratio equal to? Well, almost right. Common ratio is -3/2. Right. Another quick way to think about it is like this. Well, yeah. I mean, if you take, I mean, this is sometimes helpful for students. If you take, let's say this, well, no, let's just do it like this. If you take A2 divided by A1, that's -3/2 divided by 1, that's -3/2. If you take, so that's the second term divided by the first term. If you take the third term and divide it by the second term, that's going to be 9/4 divided by -3/2, which is 9/4 times -2/3. And again, you're going to get, that's going to equal -3/2. It will. We simplify a little bit here. Yeah, -3/2 for sure. So common ratio is -3/2. It's a geometric series. Does the series converge? Does this series converge or diverge? What do you think?
Converge, right?
Let me see here. We're getting, OPM says diverges, Clay says converges. We're getting, so I always like it when we get a difference of use. It makes it interesting. We're going to see. Yonatan, you have a question?
What R value or what end result makes, sorry, let me rephrase it. What end result of adding all the numbers up tells us whether it converges or diverges? Is there a number that we should be looking for? Because I didn't understand the definition because it clashed with another definition.
Well, since this is a geometric series, now this is for geometric series, okay, geometric series converge, right, they converge if the absolute value of the common ratio is less than 1. But in our case, we have the absolute value of -3/2. That's the absolute value of the common ratio. That's 3/2, and that's greater than 1. So our series, okay, I mean, I'll put a little now here, now. Our series, the absolute value of -3/2 is 3/2. That's greater than 1. So our series, this series here, what does it have to do? What's it going to do? Converge or diverge? So it's the absolute. What do you think?
It would have to diverge because 3/2
That's right.
is bigger.
That's right. It would have to diverge. And if you look at the terms here of the series, I mean, even just looking at it, the terms are getting like larger. They're getting larger slowly, but you know what I mean? There's no bound on the terms. They're going to oscillate back and forth between positive and negative, but they keep growing in magnitude, and it's just never going to settle down. The series will never settle down. It'll never converge. So our series diverges. Diverges. Are there any questions on that? For geometric series, once you identify the series you have as a geometric series, if its common ratio, or the absolute value of the common ratio, if it's less than 1, the geometric series will converge. If the absolute value of the common ratio R is greater than 1, then the geometric series will diverge. And obviously, we're more interested in geometric series that converge and have finite sums. Okay, who's feeling okay with that? I mean, I know you need to practice, but who at least is somewhat comfortable so far with section 8.2? Maybe give me a thumbs up. All right, Susanna is, all right. Victoria is, okay. Okay, all right, then I shall stop the recording.